This is part one of the lecture for Mrs. Roth's physical science class at the Lancaster Learning Link. This lecture will cover the first half of Module 9. In order to watch this lecture, you need to have your lab report for Experiment 9.1, your lab report for Experiment 9.3, and a blank piece of paper for taking notes. Before I get into the lecture material, I wanted to point out one change in my grading procedure. At semester time, when I sent your grades out to your parents, you may have noticed on this summary sheet that I have taken the outline out of the category of deadlines and organization and made it its own category. The reason I did this is all three of my kids are taking college classes, and last semester all three of them were required to outline some portions, or actually all of the textbooks that they were using in their classes. So it really made me think about how important it is for everyone to know how to outline well and to do that well. Therefore, I've decided to make that worth a little bit more in your grade. So you'll see that showing up here. Those outlines will be worth 100%, 100 points each, and they will all total up for 5% of your grade. So just wanted to make you aware of that change in the grading procedure this year. So let's move on to the material for Module 9, which is called An Introduction to the Physics of Motion. Now, hopefully none of you have a fear of the word physics, because physics can be a lot of fun. We're going to have a lot of good experiments to do, and physics is just a wonderful way to see how the world around us is working. Now, there's lots of different parts of science that fit under the umbrella of physics. So here I've got my umbrella of physics, and what we've covered so far in modules 1 through 8, which was basically weather and meteorology, those are under the umbrella of physics. Now, one disadvantage is that the physics that we can do here in this class is really just the bare bones because of the level of math that you have now. Physics gets more and more exciting as you learn algebra and geometry, and finally calculus is what makes it all come together. As I mentioned at the beginning of the year, and I'll say it again here, science and math go together. You just can't separate them. And as you continue to advance in the sciences, you're going to see that more and more, that your math is going to come right alongside. So it's important that your math is right up to par with what you're doing in science. Now, all around us, everywhere we look, we see things in motion. The study of motion is called mechanics, and that is really divided into three different parts. First, we analyze motion. Second, mechanics has to do with the forces that are applied to those objects. And third, it has to do with the energy that exists in them. But just like weather and meteorology were under the umbrella of physics, mechanics is also part of physics. Now, the first part of mechanics was analyzing motion. But to study motion, we have to start with the concept of position. If the position of an object changes, that's how we know that the object is in motion. Now let's look at this picture of a girl sitting at a desk with a book right beside her. Well, we can ask the question, is the book moving? Now, most of us would say, no, it's not moving. But if we were the man in the moon out there in space and we looked at that book, then what would we say if we asked, is the book moving? Well, then, yes, the book would be moving. So the fact that we can say, no, the book isn't moving, and yes, the book is moving, what does that tell us about position? Well, it tells us that position must always be given relative to something else. That something else is usually called the reference point, and it is a point against which position is measured. So if we go back and ask the question again, is the book moving? Well, with the girl as the reference point, it is not moving. But with the man in the moon as the reference point, it is moving. This leads us to a very important conclusion, and that is all motion is relative. Thus, the motion of an object depends on the reference point used to describe that object's position. Okay, so let's look at an example here. Here we are up in the mountains on a ski lift. And we're looking at that guy there that's pointed to by the yellow arrow. And we ask the question, is he moving? Well, as we've already learned, that the answer to that is relative. For example, is he moving relative to the guy sitting next to him, who's pointed to by the red arrow? What do you think? Is the yellow arrow pointing to the guy, is he moving relative to the guy next to him? Well, the answer is no, he's not. Okay, let's try another one. Now we're going to ask if the guy in the ski lift is moving relative to the little skier on the slope pointed to by the red arrow. This time, we would say that yes, the guy in the ski lift is moving relative to the guy in the green sweater. Okay, now let's do another one that's a little bit harder. Down farther in another ski lift chair, is the guy in the front one, pointed to by the yellow arrow, is he moving relative to the people in the other ski lift chair? What do you think? Well, the actual answer is no, he is not moving relative to the guy in the ski lift in the other chair. The reason for that is that the distance between them is not changing. Now, we would probably say that yes, he is moving because we're basing that relative to the background, but really relative to each other in their different ski chairs, they are not moving. So now that we have a better understanding of how we measure position and movement, let's go on and talk about speed. If an object's position changes relative to a reference point, then we say that the object is moving or is in motion. How quickly an object moves is called its speed. The scientific definition for speed is the distance traveled divided by the time it took to travel. Now, as we talk about speed, we can tend to make a very common mistake, and that is illustrated here. What's wrong with the statement if I said, our speed on the interstate was 60? Well, 60 what? 60 inches per second, or meters per day, or miles per hour? What is it? Well, most likely on an interstate it would be 60 miles per hour. But this just re-emphasizes how very, very important it is that you include the units with an answer when you're talking about scientific things or mathematical things. To show the importance of units, Dr. Weil shared a story about when he was younger, and a teacher told the students in a class that they could write notes on a 3x5 card and bring those notes in and use them while taking a test. Well, even back then, he was a stickler for units, and even though the teacher meant a 3-inch by 5-inch card, Dr. Weil claims that he brought in a 3-foot by 5-foot poster that had all sorts of things written on it that probably helped him do very well on the test. So it's kind of a funny story that if you just say a 3x5 card and don't specify the units, It could mean something a lot different than what you expected. I'm sure that teacher was surprised when he walked in with his 3 by 5 foot poster board with notes written on it. In my classes, on a quiz or a test, the numerical answer that you need is usually worth half of the points possible, and then the units are worth the other half. So make sure when you write your answer that you don't forget the units. In the book, he gave you example 9.1. A car travels 78 miles down the highway. It takes the car 1.2 hours to travel that far. At what speed is the car traveling? I want you to stop the video, pause the video, and figure this out on a piece of paper. Then when you're done, start the video again and we'll see if you got the right answer. Do not look in the textbook. Do this on your own because you need to know how to do this. Make sure that you're showing your work and that you're reporting the units in your final answer. The answer that you should have gotten for that was 65 miles per hour. That's how fast the car was traveling. So we calculated that car was going 65 miles per hour. Now we're going to convert or change the units from miles per hour to meters per second. This all goes back to what we learned in Module 1 about unit conversion. If you need to go back and review that, make sure you do, because we're going to start really putting that into practice, and it's important that you understand how to do that. So, assuming that the car was going 65 miles per hour, convert that to the speed of the car in meters per second. Pause the video, figure it out, and then when you're done, start the video again. If you did this correctly, you should get the answer that it's 29.1 meters per second. If you didn't get that, then go back to page 207 and carefully look at how he did example 9.1 and make sure that you understand what you're doing, because we're going to do another one here that's not in the book. Okay, let's try another one here to see if you get it. A train travels 85 miles down the track in 3/4 or 0.75 hours. How fast is it going in miles per hour? So pause the video, figure this out, and make sure your answer includes the units. Okay, the answer for that is that its speed is 113.3 miles per hour. If you didn't get the right answer, you need to go back to example 9.1, study that again, and try again until you get this answer. Okay, given that speed of 113.3 miles per hour, what would that speed be in meters per second? Again, you're going to do unit conversions. Here are the conversions that you need to know. Make sure that you show your work and that your units are all canceling out as they should. Pause the video and get your answer and then turn it back on to see if you're right. Okay, the answer for that is that its speed is 50.6 meters per second. If you didn't get that right, again, study example 9.1 and work on it until you get it right, or ask a parent for some help.